Let us now discuss the concept of controlling force. When the governor is rotating at a constant speed, it is in equilibrium. There is no motion of a sleeve or fly ball. Though there is no motion of a fly ball, a continuous centrifugal force will be acting on it in the outward direction and try to push it outwards. But as there is no motion, there must be an equal and opposite counter force acting to hold it in a stable position. So where does this force come from? So this force comes from, in case of pod governor, from the mass of the fly ball itself. In case of Porter governor, the additional contribution is done by the mass on the sleeve, while in case of hartnell governor, the spring force is additional contribution. Now this equal and opposite force is termed as the controlling force. Its exact value can be given as tan theta into mg plus capital Mg plus or minus small f, that is force of friction, divided by 2 into 1 plus k. This is for Porter governor. In case of hartnell governor, it is 1 by 2 mg plus fs plus or minus f into b by a. Alternatively, I can also logically say that if it is a equal and opposite force to that of centrifugal force, its magnitude will be same as that of centrifugal force, only the direction will be opposite. So I can also say that my control force is equal to mr omega square in magnitude. So from this I can plot the controlling force for the various radii of operation of a governor. So if I plot that curve, it would be this curve on this plot. AB is a plot of controlling force with respect to various radii. Let's now discuss about these straight lines OC, OC1 and OC2. What we have done is, keeping the speed constant, we have changed the radius of the fly ball, and the corresponding change in controlling force has been plotted with respect to radius. So this gives us these straight lines OC, OC1 and OC2. Now where these straight lines intersect our curve for the governor are the specific radius of the rotation for the given speed. So if the governor is rotating at the speed p, it will have the corresponding radius of r. Now what happens is, if the speed increases to p1, the radius is r1. Since there is an increase in speed, the radius is increasing. So sleeve will move upwards, the throttle valve will close down and it will try to bring its speed to the mean speed again. Vice versa, I can say that if speed drops down from p to p2, its corresponding radius will be r2, which is less than r. In this case, the sleeve will move downwards, it will open up the throttle valve and it will try to again increase its speed to mean speed p. So that is a normal operation of a governor, expected operation of a governor. So we can term this governor as a stable governor. Since each speed has some specific radius corresponding to it, we can say that it is a stable governor. That was the definition of stability we saw previously. Let's see another case. Here the plot AB is intersecting the lines of speed in some different manner. Let's see what is happening. If the mean speed is P, it is having the speed corresponding to the line OC. Now if this speed increases to P1, the radius here, if this is a radius corresponding to P and this is a radius corresponding to P1. So if you see, P1 is greater than P, but R1 is less than R. So as the speed increases, the radius is decreasing. As the radius decreases, the sleeve will move downwards and it will further open up the valve and further increase the speed. In opposite case, if the speed drops down to P2, the corresponding radius R2, which is more than R, will cause the sleeve to move upwards, which will further close down the valve, throttle valve, and further decrease the speed. So that is not how the governor should work. So from this plot I can say that this governor is unstable. It's not working properly. So this is an unstable governor. Now if you carefully observe both the plots, you see that in stable governor, the slope of the curve AB is always greater than the speed lines. Whereas in case of unstable governor, the slope of the curve AB is always less than the speed lines. So I can say that for the stable operation of a governor, the slope of the curve AB should always be greater than that of the speed lines. Then only we will get the perfect operation of our governor. So from this last point discussed, what if the slopes are equal? See here, the slope of curve AB is equal to that of the speed line. At this single speed, a governor can assume any radius in between this range. So what is this case? We have discussed this previously. This is nothing but the case of isochronism. So this is for isochronous governor. Now if I consider the friction, there will be two more curves. So my stable curve without friction would lie in between these two curves. And considering the friction, when the sleeve is moving upwards, the friction force is acting downwards. In that case, this curve will be followed. And when the sleeve is moving downwards, the friction force is acting upwards. In that case, this case will be followed. This curve will be followed. So what is the significance of this line GH? So for this line GH, if you see, the radius is not changing. That means in case of a friction, the governor will not respond unless your speed increases beyond the value N1 or drop downs beyond the value N2. That means the governor will be insensitive in between this speed range, that is N1 and N2. So from that I can term that coefficient of insensitiveness is N1 minus N2 divided by N, where this N is the mean speed, the stable mean speed with which the governor was rotating, which lies in between somewhere here.